style. It's a brand new dance called the moo cow. Hands out like this, then dip down. You know what to do now. Do the moo cow. Moo, moo, do the moo cow. Moo, moo, do the moo cow. What you know about this brand new style? It's a brand new dance called the moo cow. Hands out like this, then dip down.
That was a song put out by the Wisconsin Dairy Farming Association. Check it out. There's a great video to go with it. And this is a lovely cow. But on to interference and diffraction, which is our topic for today. I forgot to explain that song. We are getting close to rodeo season, and so I think about cowboys. And I'd already done a cowboy one, so I thought I'd give the cow its fair chance. Make sure you go to the rodeo over spring break. You need to see the calf roping. Very, very fun. Barrel racing, also good stuff. And the best thing, fried food of all sorts. Go. Anyway, today's thing is about interference and diffraction. So far we've been talking about light as if it always goes in a straight line, but we know that it is a wave, and so it does bend some. The reason why we don't see light bending a lot is that its wavelength is really, really, really small. And so to see it bend, we have to have holes that are about the same size as the wavelength. And it turns out the wavelength is really, really, really small, teeny tiny. And so we have to get small holes before we get to see any kind of interference. We know that we can't see it because we see shadows that are pretty well defined. It's only when our holes get small that we can see a little better. And we have two things. Interference is when two different things or more will either be constructively or destructively interfering, and diffraction is when they bend around. And so it's either adding together and subtracting or bending around corners, but it ends up being a pretty similar phenomenon, and the math ends up being similar. First thing I want to talk about is interference. Interference is when we have two different waves, like this one and this one. They interfere by principle of superposition. So we put them on top of each other and we see how they add. These two are in phase, and so they add constructively, get really big. These two are exactly out of phase, and so they give us a flat line. We call those in phase and out of phase, and they're half a wavelength apart. If you're talking about radians, which you do in math, it's 180 degrees, so sometimes they say that, but really we like to think of it as half a wavelength, and if they're exactly half a wavelength off, they will get rid of themselves. If they're in phase, in other words, if they're exactly the same, or one wavelength, or two wavelengths, or three wavelengths, then we get constructive. Our second phenomenon is called diffraction, and that's when light bends. And we have to have pretty small things for us to be able to see the diffraction bending of the light on the order of the wavelength. And so if you see this picture over here, you can see what the wavelengths are, the distance between the crests, and then the hole that they go through is about the same. And if we have a hole that's about the same as the wavelength, we get a diffraction pattern where it bends around this corner and it bends around that corner. If they're close enough together, they end up giving us waveforms, circular waveforms coming from like a point source there, which is the case in this one. If they're a little bit bigger, we'll get a bunch going through flat, and then we'll get a interference pattern between the stuff bending here and bending there, and we'll talk about that a little later. So our first type of interference is going to be two-slit interference, but it has to do with diffraction too, because when light comes in here, it has to be a special kind of light. It has to be coherent light, which means that all of it's going up and down at the same time. Light that's coming from the sun, some of it's there, some of it starts here, some of it starts here, and so it's not the same. But if you get laser light or a couple of different kinds of light, you can get it so it's going together. And then what can happen is we can get these two different slits of light, and then that diffracts it into circular wavefronts. In other words, it's going out in all directions like normal sound does from the coherent. And if that's the case, then we're going to have two different waves, and they're going to have different lengths that they travel. Like for instance, this right here goes from there to there and there to there. At that point, they're going the same distance, and so they're always going to be in phase. The ups are going to be the same time as the ups, so we get a constructive interference. And what this is showing us here, this is a bright fringe because my intensity is really big. But if I'm going up to this point right here, the one on the bottom has to travel farther than the one on the top, and so it gets out of phase. So that when this one's going like that, that one's going this way. And so when we do a principle of superposition, we get nothing or a dark fringe. As we go up, we get different path lengths from each one, and because they're going different lengths, sometimes they constructively interfere, sometimes they destructively interfere, so we get bright and dark fringes, which we represent by this. This is supposed to be intensity, or brightness is another way of saying it. We have a couple examples in the next frame. So here's some example pictures that go along with two-slit interference. Notice we have two slits, one here and one here, and their path lengths are shown. And if you look right across, they constructively interfere because they have the same path. If you go up a little bit, they're going to destructively interfere because the one on the bottom has farther to go than the one on the top. But if they keep going, again, the path difference gets bigger for the bottom one, and so they get back into constructive interference. Same thing goes if we go downwards. On downwards, the bottom one has less to go, but we get the same kinds of things. We like to call these the orders. This right here, these two are the 0 order. This is the first order. These down here are the negative first order. And that's just to distinguish which ones they are. These are 1 wavelength off. These are negative 1 wavelengths off. These are no wavelengths off. And so M is just telling us that it keeps going up all the way up to infinity. It keeps going down all the way down to negative infinity. You can't see them, though, because in reality, when we have the picture, they're the brightest in the middle, and as we get farther and farther and farther out, they get dimmer, and then you don't see them eventually. This one, again, has the pictures for you, and this one gives me a little bit more info in there, so you can see that. This one puts the fringes right exactly where they're supposed to be there. So this is just a couple examples of what those fringes look like. We like to draw our picture showing the intensities, and so we have directly across right there a big intensity, and then it gets smaller and smaller and smaller. These should be the same distance apart. I'm not very good at that, really. Right? And so our two sources were over here. Okay. This picture over here is emphasizing that M, the order thing. The 0, 1 is directly across from the center of our two slits. If we go up 1, it's 1, down it's negative 1, etc. This is showing me a little close-up of what's happening. Notice they're defining some things for us. D is the distance between my slits, right there. L is the length to the screen. Y is the distance up from straight across. Now, AP actually uses X there, so you should do X. And P is the point that we're talking about. And these two are our two different path lengths there. And they're saying that if I let L be much greater than D, if L gets much, much greater than D, then these two rays basically become parallel. So they redraw it here where those two are parallel. Notice that is parallel to that. And if that's the case, then we can draw a little 90 degree here, this little dotted line. If this is my theta, which it is, this is also theta in there. And then the difference in path, since these two are at 90 are parallel and this is 90 degrees, is the little bit there that I'm marking, and that is d sine theta, because d is the distance and my theta is there, and that's the opposite side. So d sine theta is the difference in path length. And that's very important for how we get our equations. So if d sine theta is the path length, if that path length is a wavelength, or if it's nothing, or if it's 1 wavelength, 2 wavelength, 3 wavelength, negative 1 wavelengths, negative 2 wavelengths, all that, it will always get a bright fringe because it'll be in phase. If d sine theta is something plus a half a wavelength, so 0, half wavelength off, or 1, 1.5 wavelengths, 2.5, 3.5, or we can put the negative numbers in, then we'll get a dark fringe because we'll be there, and since we move it over half a wavelength, we get that. We do this, they destructively interfere. And so we get two different equations, one for when we're dark, one for when we're bright, with d sine theta. And the m's are 0, plus or minus 1, plus or minus 2, plus or minus 3. Those are the equations we use to find our answers. So those first equations are when we want to find the angle up. But a lot of times we want to find actual distances up on the screen. And if we want to do that, we like to use an approximation because most times L is much, much bigger than D. In this case, X, sorry, X or D. And if that's the case, then this hypotenuse is basically going to be the same as the L that's on the bottom and that. So when we have d sine theta, we put the sine is actually x over the hypotenuse. But since it's so big, the hypotenuse is the same thing as L, and if we just put in that the sine of theta is x over L, it's a lot easier in our math. And so we go ahead and do that for most light things. We do that, we put x over L in there, and our x max, m wavelength, is going to be just m wavelength L over D. And we do the same thing for the dark spots. The dark ones, we use m plus a half wavelength. And so when we want to find the distances instead of the angles, we plug in the sine of theta equals x over L and get our answer. Now sometimes we can't do that. If L is not a lot bigger than x or D, then we have to use our trig functions to find the hypotenuse that we know. Use the hypotenuse we know to use tangent instead of sine. Makes a little bit more steps, but it's not that hard. And most times you do that is when you use sound instead of light, because in sound you can have wavelengths that are long compared to the distances that you can have. Snack time. I don't know if you remember our theme for snacks this unit, but it's things that you hide from your family. And I said last time I hid the fish jerky because my family doesn't like fish really, and they get disgusted when they see it. So that's why I had that one. My other hiding one is a little bit trickier. It was my son's birthday this past weekend. We got a bunch of stuff for his party, and he likes Doritos. We never let him get those, but for his birthday he can get whatever he wants. You know, we're that kind of family. And he got like 5 different kinds of fiery hot Cheetos. He got Funyuns that were bright red, and he got my favorite kind of potato chips. They're just like kettle chips that have jalapenos on them. And he got all that stuff, and I knew that he and his friends were going to eat all of it. And so this hidden snack was hidden in plain sight. So when he got all those fancy chips, I'm like, oh, maybe we should get something for those people that don't like hot foods. And I said he needed to get just this kettle chips with sea salt, which I like a lot. Not quite as much as the hot ones, but I know those boys aren't going to eat them. And so I hid them out there. They ate every single chip of other types, but this morning when everything else was gone, I ate these. That's right. They had not even opened these, and here I am opening them and laughing about my hiding of them. Chip for me. So, diffraction gratings are when we have more than 2 slits. If we have a transmission grating, which is this one right here, you have light coming through, and instead of having just 1 slit or 2 slits, we have 3 or 4 or 5 or 6 or 7. Turns out the same thing can happen with reflection, and that's when we have like a crystal structure and a lot of things are reflecting off, and it works the same way. Transmission gratings end up being the math being pretty simple. So here we go to the next part. As we add more and more and more slits to diffraction gratings, what ends up happening is that our maximums, these points out here that give us the biggest intensity, they just keep getting bigger and bigger and bigger and pointier and pointier and pointier as we add more and more and more slits. And then what happens to the minimums as they get more complicated down here, and there's not an individual minimum. You get pointy and then nothing. And if you had more slits than this even, you'd get one that had this point to the same place, but they're pointier, and you have craziness, pointier, craziness, pointier, craziness, pointier, craziness. The more slits you have, the pointier they get, and the stranger the minimums are. So what happens in diffraction gratings is the exact same equations as the 2-slit interference. So we get d sine theta equals m wavelength, and we get x max equals m wavelength L over D, except we don't have minimums, so we can't find the minimums, but it's much easier to find the maximums now because they're easier to see. Diffraction gratings are how they make all those little like glasses that you wear that show a little star around something. Those are diffraction gratings, transmission ones. I would do some experiments with those glasses. Our next phenomenon is called single slit diffraction. In single slit diffraction, you have only one hole, and now we call D the width of that hole. And most of the light in single slit diffraction goes straight through the hole. And so in single slit diffraction, you get one big giant maximum in the middle. But you do have some interference in this diffraction because of the bending around this corner. You get light made from this corner bending and light made from this corner bending, and they interfere. Now the interference pattern they make is a little different because it's bending and not 2 point sources. Ends up that the blue line here is the interference pattern for the 2 bending sides. And notice that there's a minimum in the middle instead of the usual maximum that we had. But that gets eaten up by the big giant maximum of the light going straight through. And so that means that we don't have a 0 order. What used to be right here was my m equals 0. And then we have all the other ones, 1, 2, 3, negative 1, negative 2, negative 3. But the equations that we had for maximum and the equations that we had for minimum are switched since the middle here is a minimum. That's what this says. That says that this is constructive, and this is destructive. Whereas normally it's the other way around. And we'll have a better better font for that later when we're talking about all of them. And notice there is no n equals 0 for this one. And so all the things we did for 2-slit interference work for this one except for those 2 minor differences. couple, three example pictures of these. This is the light coming in. You can see that most of it's coming straight through, but you do get some fringes off to the side of it. And then this is the intensity pattern for it. You can see that this one has a gigantic thing in the middle that takes over, then you get your fringes. But if you continue this pattern on, you'd get a minimum right there in the center of it. It takes these two maximums get taken up by that minimum. And then this has the 3-stage one like before. One more type of interference we got is thin film interference, and it's the kind of film that gives us bubbles, so soap bubbles, the fact that they have rainbows on them. And that works because we have different indexes of refraction. Air has an index of 1, soap has 1.5, air has 1 again. And there's light that gets reflected off the first surface, that's the green thing here, and then some of it bounces down and bounces back up, that's the pink one. And those two beams of light interfere with each other. And so if the path difference is a wavelength, then we get constructive interference, and if path difference is a half a wavelength, we get destructive. And since different frequency of light has different frequencies, different ones are constructively interfering at different times. And so the reason why this is different colors is because the width of the soap bubble is different around the bubble. Let's get into the math a tiny bit, okay? So if we say that the thickness of the bubble, and it says water there, but let's make that bubble, is T, the one that goes into it, its path's going to be 2T bigger. Now there's a tiny bit of difference in the x direction, but we're going to disregard that. We're going to say it's 2T. And then if 2T is a wavelength, you get constructive. 2T is half a wavelength, you get destructive. But we like to use this outside wavelength as a reference. And so that means that since n equals wavelength over the wavelength in the substance, we have to throw an n into our path length, making it 2nt instead. So if 2nt is a wavelength, it's constructive. If 2nt is a m plus a half, so half a wavelength, 1/2, 2.5, we get destructive. And since we can't have a negative thickness, this m only has positive values. Unfortunately, though, we have one more thing that kind of complicates things for thin film interference, and that is that if my substance comes in and bounces off of something that is harder than it is, and for indexes, that means its index is higher, it flips. Remember how we had a fixed end reflection, it flipped over? And if it flips over, that's basically getting it out of phase by half of a wavelength. And so if this one here is half a wavelength off, if this one is not, then really we need the path difference to be another half a wavelength to get constructive, and to get destructive it just has to be some multiple of a wavelength. So it changes those two things. But it really depends on the indexes. This is low, high, low, and so that's this time. But if it was low, higher, highest, then it changes, and so we have to have two different types of thin film. We call the first one a soap bubble because we have low, high, low, and we know that this first one flips right here, that's the red part. The bottom one doesn't, and so that means that since I'm out of phase from each other, if I have m for my path length, which is 2nt, that's going to be destructive. So it's already been flipped, one of them's been flipped, one of them hasn't, so if the path length is exactly a wavelength, they're out of phase. But if the path length adds another half in to get them back into phase, then we get constructive. Now if we get an oil film, which is like oil on top of water, we have an index of 1, 1.5, 1.7. So it flips on both of them. So they're both flipped over. If they're both flipped over, then if my path length is m wavelength, then I get constructive, and destructive is m plus a half. And so I essentially flip those two equations if I get different order of indexes being higher or lower. That's a little confusing. I'll talk about that in class. And so again, interference is what causes some of the rainbow patterns that we see in water. In this case, it's oil on top of water. Why it makes those little rainbow patterns like this up here is because we have different thicknesses of film, and they're constructing with red, then yellow, then green, then purple. So that's why we get the little rainbows. Turns out that air in between higher indexes also interferes. And so if you have glass, the air film, and then glass, like if you put a lens on top of another piece of glass like this, you get interference. And since when you have a lens, it's supposed to be spherically round, you know, like that. If you put one on top of the other, you should get perfectly spherical lines here. And if you don't, then you can grind down one side. And that's how they get the lenses that we use in class so perfectly spherical, if you ever wondered. And the person that figured it out was Newton. That's why they're called Newton's rings. Holy cow, we got a lot of interference, we got a lot of diffraction, we got a lot of M's, we got a lot of D's, we got a lot of things. So we made a little chart for all of them. so you can see. And so this is the type of diffraction: 2-slit, diffraction grating, 1-slit, soap bubbles, oil slick, and then there's a picture to remind us of what each one is. 2 slits going to that pattern, multiple slits going to spiky ones, 1 slit going to a big middle, make sure and draw the little ones that are overrun, and then the different indexes for soap bubbles and oil slick. And then we have an equation for constructive and destructive, and notice with the diffraction grating and the slit, we have both the angle and the x, or the distance up along the screen. For soap bubbles, we just have the path length differences. And being able to draw up this table by yourself, and I would draw it out, really helps you keep them in mind. And remember that the M for the first one is 0, all plus or minuses. Same thing for diffraction grating. Difference in diffraction grating is we have no destructive, remember. Single slit diffraction, notice we flipped our constructive and our destructive equations. This equation went to that one, this equation went to that one. And the soap bubbles and the oil slick are also flipped. And those just go from 0 to 1, and there's no 0 on our single slit diffraction. This is a great chart. We'll probably make it again in class just to make sure we get it. But that's all we got this time. Don't forget the rodeo is here over spring break. Make sure and go. Here comes the last bit of the moo cow. Look for the video.